We're going to continue our discussion of using polar coordinates to compute double integrals. Last time we saw how to integrate over polar rectangles, and we looked at a specific example of doing that. In rectangular coordinates, we generalize to type 1 and type 2 regions. For instance, if I was given a function f and a type 1 region R, then I could define the double integral of f dA over this region R as follows. Basically what I did is we have these boundaries. The x bounds are constant. So here I have A and B. But the y bounds aren't constant. They're given by these two curves, y equals g1 of x and y equals g2 of x. But what I do is I just find a lower and upper bound for this region, say C and D. So C is a lower bound for g1 of x and D is an upper bound for g2 of x. And then I have this larger region, and now I'm just going to integrate a slightly different function over this bigger region. So what's this different function? Well, I call it f bar, and f bar of xy is defined really just in terms of f. It's equal to f of xy if I'm inside the region R. And then basically I just want to turn the function off when I'm outside the region R. So I'm just going to set it equal to 0 otherwise. Okay, so then what we did was we defined the integral over R of f dA. We defined it to be the integral over this rectangle of f bar. So we're integrating f bar. And now we can get more specific because it's a rectangle. We can write it as an iterated integral from C to D, from A to B, dy dx. Okay, so we essentially define it as the integral over this rectangle and then apply Fubini's theorem for integrals over rectangles. But then, of course, we can realize that if I pick a value of x and I look at this integral from C to D of f bar, well, f bar is 0 here, and it's 0 from here to here. And the only place it's non-zero is from g1 of x to g2 of x, and in that case it's equal to the function f. So what we concluded was that if my region R is given by, x is bounded by two constants, a to b, and y is bounded by two functions of x, g1 and g2 of x, then this double integral, which in the end was defined from the integral from C to D of f bar, really is the same as integrating f from g1 of x to g2 of x. And then this is the iterated integral that we would actually calculate. So that's the situation for rectangular coordinates. Now we want an analogous situation for polar coordinates. So the polar region that we need has a similar form. So we're going to want theta to be bounded by two constants, say alpha and beta. And then for each value of theta, R is bounded by two functions of theta. So the picture of that is exactly this. So here we're still in the xy plane, and we can see that this region is bounded by theta equals alpha and theta equals beta, these constant lines to the origin. Okay, but then for each value of theta, R is bounded above by g2 of theta, and it's bounded below by g1 of theta. And so if we pick a different value of theta, these bounds vary based on which theta that we pick. All right, so this is sort of the analogous notion to a type 1 region, or say a type 2 region, depending on how you want to think about it. But the idea is that one of the coordinates is bounded by constants, and the second coordinate is bounded by functions of the first coordinate. Okay, so suppose we have a function defined on one of these polar regions. Okay, so R is of this form that we just discussed. So it looks something like this. Now we want to define the double integral of f over R dA. So we're going to do the exact analogous thing to what we just discussed. We're going to bound this region R that we were given by now a polar rectangle. So this is our region R, and now we've bound it by a polar rectangle where the lower bound is, say, A, and the upper bound is, say, B. So these are R values. R equals A and R equals B are these circles. And we've bounded this region R by a polar rectangle, and now we're going to use the same sort of trick that we did before. So we're going to define this new function f bar, and it's going to equal f inside of R, and it's going to be equal to 0 outside of R. Okay, and so now you sort of know how this is going to work. We're going to define the integral over R of f dA. We're going to define this to be the integral of f bar over this polar rectangle, and now we can apply Fubini's theorem in polar coordinates, and it's going to be the integral from alpha to beta, the integral from A to B of f bar at r theta times r dr d theta. Okay, this extra r term shows up in polar coordinates. We've seen that before. All right, so as before, we can simplify this because right now we have these constant bounds, a to b, for this function f bar. But just as before, if we look for one of these values of theta, the function f bar, it's equal to f inside of R, and it's equal to 0 out here. So we can safely ignore everything outside these ranges. So if the only thing that matters is from g1 of theta to g2 of theta, and in that case, this function f bar is the same as the function f. So in the end, what we have is this double integral that we're interested in can be computed with this specific iterated integral in polar coordinates. So now we've essentially generalized the case to the most general polar region that we're going to be interested in, and to look at even more general regions than this, what we'd essentially try to do is break them up into polar regions that have this form and then apply this technique. So all of the examples that we'll go through in this course will, when we use polar coordinates, will be iterated integrals of this form.